and you look at the point sources of where all these things are coming from, people burning coal for electricity or burning gas to power their cars and vehicles, the manufacture of Portland cement is the single largest point source of any other industry on Earth. 8% of all global warming comes from that. If you take the fly ash, which is this waste product from the coal industry, if we take that and put it in the concrete, it solves two problems. One, it eliminates a waste material, which is great. But two, it's less Portland cement than we need to use, and it makes the concrete more workable. And so what you're seeing with the Superior Wall is one that has both. It's, half of the Oreo cookie is insulation with these metal ribs in it. The inside cream filling, I guess you could call it concrete. So you're getting a strong high thermal mass wall with a lot of insulation. And then about 30% of your home's energy is escaping out of those windows on average. And not just through the glass, which is a terrible insulator, but in older homes, the cracks around windows and doors make a home very drafty. In a typical older home, and I would say that's a home built before 1980, if you added up the surface area of all the cracks around all the windows and doors, you'd have an area about the size of a small window.
Welcome to Mindful Businesses, Our Sustainable Home, and I'm your host, Vidya Iyer. In our latest series, Our Sustainable Home, we talk about options, solutions, and resources in the construction industry to make a home sustainable. Mindful Businesses since 2019 has featured several sustainable innovators, businesses, and thought leaders. But we realized that the process of building or making a home sustainable is at best confusing and ever evolving. In continuing our conversations on this topic, we have today on our show an expert in this field, Eric Corey-Fried. Eric Corey-Fried is a lead fellow, principal, director of sustainability at Canon Design, Living Centered Design. He joins us from Portland, Oregon. Welcome, Eric, again on the show.
Oh, thanks for having me back.
As we continue our conversations, it's the third time that you have come on our show, and we rely on your knowledge, your expertise to guide our listeners to make their home sustainable. In our earlier episodes, we talked about the basics, the direction a home should face to match the owner's lifestyles, the types of wall construction, insulation options, and so forth. In this episode, I'd like to talk to you, ask you to touch upon some of the other components in home construction. In particular, the use of cement. The cement industry contributes to about 6 to 8% of the greenhouse gases that are emitted every year. Could you explain to our listeners what is the process of making cement, which then is used to make concrete, releases the greenhouse gases and emissions such as mercury and other gases?
Yeah, you kind of nailed it. It's hard to imagine building a building without concrete. It usually shows up somewhere, typically in the foundation, but also we will build the whole structure out of it. At the surface, concrete seems like a great material. It's an ancient building material. The ancient Romans built the Pantheon out of it in 79 AD using their own special mix of concrete and cement, and that building's been around for a long time. Also, it's obviously durable, somewhat fireproof, pretty great in an earthquake, can be its own finish. It's also technically all natural. The first blush, concrete looks like a wonder material. In many ways it is. But its chief ingredient, Portland cement, it's mined out of the earth, it's heated to 5,000 degrees. It just requires an immense amount of energy in order to manufacture it. And as you noted, it's responsible for about 8% of all carbon emissions. So in other words, if you think about climate change and you look at the point sources of where all these things are coming from, people burning coal for electricity or burning gas to power their cars and vehicles, the manufacture of Portland cement is the single largest point source of any other industry on Earth. 8% of all global warming comes from that. So as architects, we want to see if we can find something else. So there are things that we can do in the concrete to lessen that embodied carbon, those related emissions, or we could avoid concrete altogether and try something else like mass timber.
But who will build the cat, right? We are building a home. I am pretty committed to sustainability. I know there are options which we'll come to, but even I don't have the guts to say that, hey, I'm going to build my foundation of X or Y or Z product. So who is going to start doing this?
We've already started. I first started experimenting with using alternative mixtures back in the 90s for stuff. This has been around for a long time. And if you think about it, the majority of what makes concrete concrete is it's a giant mix of sand, stone, water, and Portland cement. Portland cement is what we call the catalyst, right? It's the glue that holds it all together. So there's a lot of other stuff in concrete that makes concrete what it is. But if Portland cement is the issue because of its embodied carbon associated with it, the question becomes, could we substitute something else? So you could still build out of concrete, but maybe lessen some of that Portland cement. And so in the early days, we used a waste product called fly ash as an alternative to cement. And it was basically a 1-to-1 ratio, right? For every cup of fly ash we put in, it's a cup of Portland cement we don't have to. But it's also a 1-to-1 ratio in that every pound of Portland cement we use is a pound of CO2 that we produce. So it becomes a very easy, math problem. If you take the fly ash, which is this waste product from the coal industry that normally we dump into the ocean or into the air, if we take that and put it in the concrete, it solves two problems. One, it eliminates a waste material, which is great. But two, it's less Portland cement than we need to use, and it makes the concrete more workable. So we found that it's a giant chemistry set. And so over the last few decades, a lot of people have been experimenting with what other things could we put to replace the Portland cement with some other alternative cementitious type material. And now there is a wealth of cool things that you can put in there that all lower in that carbon profile.
Yes. So, for instance, we have had on our show, I think, a very cool innovator. He uses silica flume and sand, and the gentleman's name is David Stone, and the name of his innovation is Ferrob. What percent of green cement is being used presently?
Well, it's hard to say because it changes every minute, but let's put it this way. Every concrete manufacturer in the world is already giving you some sort of alternative cementitious material to replace the Portland cement, in part because it's cheaper. The way to think about it is it's like in the movie Scarface. If you're a drug dealer selling cocaine, you mix in baby powder in your cocaine a little bit to help stretch it out. That's kind of what they're doing a little bit with replacing Portland cement, which is expensive, with something like fly ash or silica fume or slag or something like that. So everybody's getting around 15% anyway. Typically, you could up that to 35%. So that's 35% less carbon emissions and replacing with something else with really no cost differential. Once you go past 35%, it starts to change some of the structural qualities of the concrete. So you'd want to check with your architect or structural engineer to make sure it works. It also changes the appearance slightly. These are not huge obstacles, but still something to consider. And then, of course, that's just one strategy of playing with the mix. There are other strategies that we can play with to lessen that environmental impact of concrete, everywhere from changing how we use the concrete, lessening the amount of mass that we use, building voids into the concrete, right? Just lightening the building. And then, of course, trying to eliminate concrete entirely with some other material. And all of those options are on the table. And sometimes we'll do a mix of a little bit of all of them.
In our home in particular, we were looking at how to reduce concrete. And of course, in Western New York, one of the main things that we use concrete is for the foundation. So let's focus on foundation and basements. There are different kinds of basements. So you're an architect. Talk about in a home, what role does basement play aesthetically and also structurally? Like, how important is a basement?
A basement is a tough thing because on the one hand, I grew up in the East Coast. I have very fond memories of having a basement in our house. And on hot summer nights, I would sleep in the basement to stay cool. Most people who have basements think of them as kind of these giant storage areas or playrooms. Sometimes they'll refinish them into something. But let's look at what a basement's really doing. You're excavating a 1-story deep hole into the ground. So it's already more expensive than building above ground. It's also very limited in terms of the amount of daylight and windows that you can do. There are what's called daylit basements where kind of half of it is stuck into the ground, the other half is open on one end. Those are kind of a little more flexible. But in sticking this essentially concrete swimming pool into the ground, you have to resist two major forces. One is the upward force of groundwater wanting to push the whole building up. And two, all the rainwater that soaks into the soil creates what's called hydrostatic pressure. It's pushing on the walls. So the walls have to be strong enough to resist the upward force and then the sideways force. Now, we've been doing this for centuries. It's not a huge deal. It's very easy to do. But we essentially design those walls to shed that water as much as possible. And so there's a lot of, I don't want to say tricks, but there's a lot of builder strategies that we all employ to make basements possible.
Sorry, possible and dry and not very cold.
Well, so think about what a basement is. Because it's stuck into the ground, you've got these concrete walls surrounded by earth. So we have what's called a lot of thermal mass around it. The reason why I spent my summers as a kid sleeping in the basement is because all of those earthen walls and concrete around it stored a lot of cool energy. So it was a cooler place to sleep simply because it was basically underground, right? The same reason that we used to have root cellars as a kind of a natural way to cool food and keep it cool, even in the summer months. That's essentially what a basement is. But we do a lot of work to make that possible. And then there are, of course, states like Florida, where their water table is so high, they virtually never build basements just because it's not worth the trouble, even though it's a hurricane state. And it would make a lot of sense to have a safe place like a basement to do it in. But the ground doesn't really support that in a state like Florida. So, it's a give and take. It's a little bit of a pro and con, right? It's nice to have the storage and additional square footage without having height. But on the other hand, generally a difficult place to furnish and make it feel cozy, having no natural daylight and kind of, limited access with just a stair. So you have to design the basement in a way to make it, in my mind, very livable.
And if you're lucky enough to have the slope in your lot to allow for a walkout basement, then you have more light and will make that place more livable.
The other issue with basements is some of them are more serious. So on the East Coast, we have this phenomenon called radon. And radon is a radioactive gas that naturally seeps out through the ground. Normally not a big deal, happens all the time. But with basements, because they tend to be kind of small windows that tend to be closed, that radon gas, that radioactive gas can build up. And so if you live on the East Coast, you've probably been told to get a radon detector for your basement. Pretty normal thing. And it's almost like a smoke detector, just alerts you. And it's very easy to fix too. You can simply just open the windows and flush that building, that basement with air. But now, because we know so much better, for newer buildings, we ventilate the basements specifically for radon to just try to eliminate it. To me, it's a very good example of humanity creating a problem unknowingly and spending years trying to find an easy way to fix it. And putting basements in the ground with radioactive gas is a good example of that.
We decided to have a basement for all the reasons that you've listed. Per square foot, it costs much less to do a basement than the story's about. But I always struggled with the thick basement walls. How thick are the normal basement walls? 9 inches or 7 inches?
They're concrete blocks, so typically 8 inches.
We tried to look for more alternatives to see how we can reduce our home's consumption of cement and thus concrete. We came across this very innovative solution called superior walls. Have you used it in any of your projects?
Yeah, back when I was doing residential, what I like about it is I love anything that's prefabricated. The idea of these kind of precast walls that come in and just slide into place really lessens labor time, speeds construction. I mean, things like that are just great. There's a lot of alternatives that are just great.
Yeah, and the walls are so straight. At some point, I will post drone videos of the walls of our basement. I don't know if you can ever get that in poured walls or if you can get that when you build the cinder blocks.
You're the first person to really comment on the straightness of them. They're pre-manufactured, pre-engineered things, so of course they're straight. If you think about it, yeah, it makes a lot of sense. They also come in standard construction widths because, believe it or not, that's pretty important because everything in construction is some module of 8 inches, right? Bricks are 8 inches wide, concrete block is 16 inches wide, studs are typically done 16 inches on center, plywood comes 48 inches wide. So if you really lean into that module, that 8-inch module, design the whole house to be based on some module of 8 inches, you can also eliminate waste, speed construction, lower cost. And so Superior Wall is a good example of that as, this kind of prefabricated thing that just zips up quickly.
Yeah, it basically took them 3 days to put together. They came to spec out the site the day before. We had the plans drawn up. But what attracted me to this is that the walls are only 44 mm thick, the concrete portion of it. Then you can explain how these walls actually stand up and are able to hold up the whole house above it.
It's not a trick or anything. Basically, anytime you're building out of concrete, you typically either need to make a form, what we call formwork, and then you fill it with concrete, and then the form has to be a certain thickness, or you get something pre-made like a concrete block. A product like Superior Walls is essentially getting the best of both worlds. It's an engineered frame made out of steel, which adds to the strengthness so you can go thinner, but you're still filling it with concrete, and the concrete's going through all of the panels in it. So it's what we call monolithic. So it's acting as a single wall surface, and the metal frame is making it stronger. And then they do a few other things in terms of the top and the bottom are held in place with a steel, what's called rebar, reinforcing bar. And all those things combined make for a relatively thin but very, very strong wall.
So, in my layman terms, the way I understood how the superior walls, even though they are only 44 about 2 inches thick, are able to hold up is you have those collapsible cubes, where you store your stuff and things like that. When you open it up, you have, some structures to it. It's thin, but it has structures. But till you push the floor, the base of the cube down, the thing doesn't stay up. So, in case of superior walls, you have these reinforced steel walls and insulation attached to this 44 concrete, and you set it in the very thick gravel, no footers, and you have to pour the floors, which is kind of holds all these walls, pour the floors with cement, and then backfill in from the outside. Does that make sense? Like, for me, it probably is very basic, but for a non-technical person like me, that's how I was able to convince myself, yeah, this really thin wall will be able to withstand the pressure from the outside, hold my home from the top.
Oh, that's interesting. By pouring the internal slab, what we're doing is we're creating another piece of monolithic concrete that's holding the sides apart, essentially, so it keeps it from collapsing. And then we're filling the walls, and those are also monolithic. That's basically it. You're still, at the end of the day, building a box into the ground or a swimming pool into the ground. What's great about them is they're addressing the things that I talked about earlier. The gravel around the perimeter of the basement is all designed to shed water. We don't want water building up on the side of any basement walls because it creates that pressure. So basically gravity takes it, runs down to the bottom, and then the gravel gives it an escape. There's also, I don't know if you got to see it, but there's also a big perforated pipe that's running around your entire house. And all of that's designed to whisk the water away, just get it all away. That's kind of our solution to dealing with heavy water pressure in a building is we let it soak into the ground and then we take it far from the building and then you prevent leaks. But you'll have a watertight, perfect basement for, a century if you install it right.
And also from the homes that I've visited, which have superior wall, there's very little variation in the temperature between the first floor and the basement.
Well, the insulation really helps. Concrete in general has a high thermal mass, meaning it stores temperature really well, but does not have that much R value, that much insulation value. We typically have to add insulation to concrete in order to make sure that all of our heating and cooling doesn't escape out through the walls. And so what you're seeing with the superior wall is one that has both. It's, half of the Oreo cookie is insulation with these metal ribs in it. The inside cream filling, I guess you could call it concrete. So you're getting a strong high thermal mass wall with a lot of insulation, and then the water's draining down the side of it. So it's very quick to put up and maintain.
So people who do not have access to superior walls, what would be the next best sustainable solution for basements?
So one of the other products that I love is this one called insulated concrete forms, also known as ICFs. And the nice thing about ICFs is you can use them for all the walls in the building. So you can continue going up. And depending on what your state building code is, you can do 2 or 3 stories with them, which is pretty cool. What they look like is they look like styrofoam Lego blocks is what they look like, because that's kind of what they are. They have kind of Lego-like teeth at the top and the bottom. And so these lightweight hollow styrofoam blocks can be cut just with a simple handsaw to any length. And so you fit them together nice and neat. You get them perfect the way you want it. And once they're perfect and everywhere you want them to be, you then fill them with concrete. So they're essentially like a formwork, but that formwork stays in place because that styrofoam creates a nice thick band of insulation on both sides of the wall. It's very easy to maneuver. You set it in place, fill it with concrete, and boom, you've got kind of an instant wall. They're just as straight and true as what you're seeing with the superior product too.
So let's compare the cost, right? Cost of poured concrete blocks, ICFs, and superior walls. Which would be most cost, because it is also a balance, right? At some point, in when people are building a home, where do I put my money? Do I try to make it more energy efficient or?
Well, think of it this way. They're not an apples to apples comparison. If you think of a traditional basement as being built out of concrete block, CMU it's called for short, concrete masonry units. A traditional one's being done that way. What you're getting kind of the bare minimum basement, but it's probably not very well insulated. In fact, what people typically do is they come back and finish and add insulation and drywall to that. So you want to make sure you're really doing a true apples to apples comparison. A bare concrete wall, block wall, will have a worse performance over time than, let's say, one of these more engineered products like Superior or an ICF. So just factor that into your thinking. But CMU would probably be the cheapest just because of material and labor costs being what they are. You get these other advantages on top of it. And once you factor them in, I think you'll find that they're almost at parity, especially with an engineered product, which speeds up construction time so much.
In case we want to refinish our basement, in case of superior walls, all we have to do is just put up drywall because the insulation is already there. The steel studs are already there. And I could finish my basement, literally. It's that simple. So it's the upfront cost of having the insulation and the studs, whereas in the CMUs, you would probably spend that later.
The CMU is also not technically what I call a monolithic wall because you're stacking up blocks. We do tend to stick some rebar in and fill the grout, the cells of the block with grout, but it's not as strong of a wall as you'd find with a complete poured-in-place concrete wall like you get with the Superior product or the ICF product or even a real full concrete product. The other thing to factor in mind, and this just makes everything more confusing, is that all of this varies widely by the local labor market. So what you find is that in Virginia, you might get a different price than you would in Georgia versus New York versus whatever. As with anything, do your homework.
Let's move on to other parts of the house. And, when we spoke about how to make a house sustainable, we talked about how we should try to focus on enveloping the house in such a way to reduce energy. And we talked about the walls, the stick buildings with the insulation. An important component of this enveloping are the windows. So let's go to fenestration. There are so many different kinds of windows. If you think about it, a long time ago, like I'm in this, right now I'm recording in a home which is built in the early 1900s. It has very few windows because the windows were considered a place where air leaks in and out and increases your electricity or your gas or increases your energy costs. But now we have better windows and we are able to put more windows and use the windows potentially to even reduce the energy consumption, right?
Think about windows for what they really are. They are a technology, just like anything else in the building, right? It's a construction technology, but it's a technology. And if you look at older homes, think of like an old Victorian home from the 1830s or something, we couldn't produce glass in the sizes and quality that we can today. The technology was rather limited. So windows tended to be small because of price and because of available technology. So a Victorian home tended to have rooms with small punched windows with very limited access to light and air. It wasn't because that's what they wanted. It's because that's what the technology available at the time was. Now, of course, we can produce expansive pieces of large glass. We can make an all glass house if we wanted to. And you might be thinking, well, why don't we do that? Well, there's a couple reasons. Number one, not everybody wants to be that open, right? They don't want people to see into their homes that far in. The good thing about glass is it allows in light and view, but the bad thing about glass is that it also lets in light and view. You might not want light and view all the time. On a summer day, having an all glass building would bring all that heat gain to it. And so what we found is try to find a balance of what's the appropriate mix of privacy with openness, with daylight, with access, with fresh air. And so modern homes today tend to be a little more open, but it always drives me crazy when people spend all this money on big, expensive windows and then have blinds that are down all the time and don't even enjoy them. So you want to make sure that if you're spending the money on the windows, you're at the very least going to use them well. And then about 30% of your home's energy is escaping out of those windows on average. And not just through the glass, which is a terrible insulator, but in older homes, the cracks around windows and doors make a home very drafty. In a typical older home, and I would say that's a home built before 1980, if you added up the surface area of all the cracks around all the windows and doors, you'd have an area about the size of a small window. So imagine all winter long leaving a small window open, and that's what the cracks around all of your openings in an older home is doing for you. Now, there's ways that we can handle this, ways that we can deal with it. We can get some, caulking and, fill up those cracks and make the home a little more airtight and make it less drafty. That's a smart thing to do. It'll pay for itself in a matter of weeks. But if you're building a new home, you want to find this smooth balance between how much window and exposure and light and heat and privacy do we want, and how much do we want a well-insulated building. In addition, the technology of windows has improved. So instead of just one pane of glass, you can get 2 panes or even 3 panes of glass. And they're so well engineered now that we do have windows that have the same insulative value as the wall itself. So instead of losing 30% of your heating and cooling out of those windows, these much more expensive windows can hold all that in, and they tend to pay for themselves over time. But if you invest in windows and insulation, that's really the recipe for high performance skin on the building.
I want to move a step further as to how to use windows to reduce your energy costs. So, for instance, in Buffalo, New York, our springs and falls are pretty long, and we could technically do away without using the air conditioning. But if it's a really sealed, tight home, I would probably need the air conditioning on every time the temperatures go above 75 or 80. But if you have a window, the technology and the position of the window in such a way that you can actually moderate the temperature in the house without ever switching on the air conditioning or even the heater for that matter, maybe because in winter you could have southern facing windows, which will help heat up some of the spaces.
Now you're starting to touch upon the fine art of what we call passive solar design, the kind of the fun part. If we know that windows let in light but also heat, how can we take advantage of that in the winter when we want to be warmed up? And how do we avoid that heat in the summer when we don't want to be heated up? And so a typical textbook passive solar strategy in a place like Buffalo would be that you'd have expanses of glass that face south, but an overhang, so that way the winter sun, which is lower in the sky, can come in and warm up the building, and the summer sun, which is higher in the sky, is blocked by that overhang. That's kind of a typical, very simple, easy thing to do. And we know where the sun is every minute of every day. So even calculating how deep to make that overhang I can do that in 30 seconds, right? So it just becomes this easy thing to do. And then if you know the sun is going to come into your building in the winter and warm it up, then give it a chance to do that. So have it hit a floor that's made of some sort of big mass material like concrete or stone or tile. So the sun will hit that for the bulk of the day. It'll warm up that floor. That heat will be stored in the thermal mass of the floor. And then at night, when the sun drops, you'll be able to release that heat and keep the building kind of relatively cozy all winter long. And then the reverse is true in the summer, right? You have the overhang. The sun is not hitting that floor, so that floor is in shade all day, and it'll stay cooler. And that thermal mass will store up the coolness and then keep the house cool all summer long. And then you top all that off with what we call passive ventilation. You have a window open on one end, you have another window open, hopefully higher on another, and you get air moving and circulating through the building. And suddenly you've got a formula for a building that can really maintain its temperature for pretty much 12 months of the year.
Having said that, and the fact that I like to leave windows open, I also don't want to run around the house every time there's a shower. Every time it rains, I have to literally run around the house trying to make sure all the windows are closed so that the water doesn't come in. So then I started investigating. I spent so many hours. I would have spent about 200 to 300 hours investigating windows, getting bids, comparing them, the triple pane, the material of the frame. And I landed upon the tilt and turn windows that are very popular in Europe. Primarily, one of the main reasons is that I could have the windows flip inside. Imagine a window which is fixed at the bottom and it flips in. In fact, if it rains, the water just drains out. It doesn't come inside the house. And we had to import these because there are very few manufacturers of tilt and turn windows in the United States. Why has the technology for windows, like the technology for building a house, so far behind? Why are they not adapting to the needs, and especially with climate change?
There's probably a few reasons, but believe it or not, probably one of the biggest ones is just tradition. We don't think of windows as losing a third of our energy through them. We think of windows as an amenity, right? As this thing that we look out and see sunlight and so forth. By the way, one of the other advantages of the tilt-in windows, my clients have told me, is that they love to clean them. they tend to be kind of neat freaks, and they by leaning them in, you can kind of clean the windows without having to get on a ladder. So they like that. There's also other ways to do that where you can have the windows open on a rainy day and still capture the breeze, including thickening the walls, adding more overhangs, and so forth. But I think the solution you came up with is great. The windows in Europe, as you found, are much better than the windows here, generally speaking. Part of it is the way they handle regulations. Part of it is kind of the mindset there of European cities tend to be older. They're used to retrofitting older housing. They know how inefficient and drafty these older buildings are. So putting in new windows, their mindset around them is still different. I think in the States, that mindset isn't that prevalent. So, we're not making those connections.
And also, energy costs are significantly higher in Europe compared to America. Is that correct?
Well, they're getting pretty high here. They're pretty expensive here too now. I think people have kind of forgotten how cheap energy used to be, but if they haven't looked at their bill lately, it's a lot.
But when a person is making a decision about windows, we talked about glazing, which is the glass part. Then we talk about the frames. So you have the wood frames, you have the aluminum frames, you have fiberglass, and you have UPVC, which is a little bit different than PVC from the research that I've done. It's basically PVC with, correct me if I'm wrong, what I was told is PVC with steel reinforcements holding up the PVC. So they're a little bit different than our traditional vinyl windows that we have in America. So in terms of the structure. So we have all these materials, wood, UPVC, fiberglass, aluminum. Rank them for me in terms of thermal loss. But I also want to say that's not the only factor that you may want to take into account while making a choice.
Generally speaking, there's a fourth option that you didn't mention. That's kind of a variation on one of them. But let's just go through each one. So wood window. Wood windows traditionally are what we used to build windows out of because that's what woodworking was, right? Making things like cabinets and windows. On the one hand, wood is a great natural insulator. We build houses out of wood. There's a nice touch to it. People like touching the wood windows. They're also naturally thermally broken, meaning that on a cold day, the window won't transmit all of that cold into your building. But it's wood, so it needs to be painted. If you paint anything that's exposed to the outside, it needs to be repainted, every 3 to 7 years, depending on where it is and how much sunlight is grilling it. So on the one hand, people love wood windows because they romanticize them. On the other hand, the maintenance costs can be a lot. The cost of the windows themselves are expensive, but they'll last forever. So it's, you have to weigh what your priorities are. My favorite alternative, and what I did a ton of, what's called clad windows. So it's a wood frame, but on the outside, it's clad with essentially a metal covering. And you can get that covering in pre-made anodized colors, so you never need to paint them. So it makes that window virtually bulletproof. It's also the most expensive window you can buy, but a wood-clad window gets the aesthetic performance, the energy performance, and certainly the maintenance performance I think you'd want, but you're paying a premium for it.
But what about seepages between the aluminum clad and the wood? We used to have a Pella aluminum clad windows in our previous home, and there was class action lawsuit against Pella actually, which they settled, where the water seeped behind the aluminum and rotted all the wood in between. People have to be aware that when you buy a product, make sure that it's manufacturer warranting against such seepage.
For residential windows, the top three are typically Pella is one of the ones that always comes up. So is Marvin, Anderson. Those three tend to be kind of the top of the line. And that's on the wood and wood-clad windows. Then there's aluminum windows where the frame itself is aluminum. What's nice about it is they're cheaper, they're lighter. But the trouble is aluminum is, on the one hand, is an alloy that doesn't technically rust. But on the other, it expands and contracts a lot based on temperature. Aluminum has a very high expansion contraction based on temperature. And because of that, the windows tend to shrink and expand all day long. In addition, they traditionally were not thermally broken, meaning that if it was a cold day, the entire aluminum frame would get freezing cold and it would radiate that cold into your house. When I was a kid, we had aluminum windows, and I remember in my bedroom, condensation droplets from the air would freeze on the windowsill. And so I'd get icicles forming on the windowsill that I would sit in bed and play with as a kid. That is a non-thermally broken window. Now we don't do that. Now we have aluminum windows that have a little plastic thing all around so the cold doesn't creep in. So that makes it better. But they're, again, don't need to be painted because they come in a color. So, the maintenance is fine. But that's kind of the next tier down. And then the third bucket is vinyl. And there's polyvinyl chloride, vinyl, PVC. They all have different names, but it's all essentially the same thing. And then the UPVC is just, there's no steel in it to my knowledge. The UPVC is essentially softer, so it doesn't get as brittle in the cold and doesn't fade in the sun. PVC also tends to be thermally broken. The trouble is the PVC, from a health perspective, is the worst of the lot. PVC or polyvinyl chloride is toxic at every stage of its life cycle. In a fire, one of the compounds that's released from burning of PVC is arsenic. It's just an awful material, but it's very, very cheap, which is why we make cheap things out of PVC because it's a cheap material, and so you get cheap windows from it. But those are the three tiers: wood, aluminum, PVC, kind of in that order. But it's also a matter of where you live, right? If you're living in New York, you get pretty severe winters. It's to me worth investing in good windows for that. If you're living in a temperate place like LA, it probably doesn't matter as much.
So we actually are leaning towards getting aluminum windows. I didn't want UPVC, though it's more reasonable. So we kind of compromised on the window options that we have. I'd like to tell our listeners that when you're trying to price out windows, you can save a lot of money by changing how you design the windows. So some of the windows, we made them picture windows. I knew that I would never ever open them, but I need light. So we played around a lot, and that's why I spent the few hundred hours on these windows with different window manufacturers, and arrived at a balance which matched our budget, gave me the U values and R values that helped our overall goal to build a sustainable house. So let's very quickly talk about U values, which are different than R values.
This is where it gets really confusing. There's also K values, which I won't get into, but so R values are what we typically think of in terms of insulation. In fact, if you go to a Home Depot or a Lowe's and you see insulation being sold, whether it's rigid board insulation or the pink fluffy stuff, it comes in an R value. Why an R value and not an I value for insulation? That's a whole long story too. But the higher the number, the higher the insulated value it has. But each material in the wall has an R value. So when we look at the total building, it's not just how much insulation we have, if that insulation is, let's say, R19, but then if you think about it, on one side of that insulation is also drywall, and then paint, and then a layer of air, right? On the other side is usually plywood and some sort of siding. And so we measure the entire wall assembly of all that stuff, insulation and all the other stuff on either side, and get a total R value for that insulative capacity of that wall. Very easy to measure. Well, you can't really do that for windows because windows are complex. Part of them, as you've noted, are glass, glazing, we call it. Some of that times that glazing is 1 layer, 2 layer, 3 layer. Sometimes we fill between the glazing with a gas that helps insulate it even more. But then there's the frame. And so a small window that's only a little bit of glass and a big frame will have one insulative value, but a big expansive picture window that's fixed is mostly glass with a little bit of frame around it. And so the way we deal with that is we do a total value that we call U value. Technically, U value is 1 over the R value. But if a wall has an R value of, let's say, R19, a window would have a U value of 1 over 19. The idea is that windows generally have a much less insulative value than a wall ever does, even if you get triple pane, whatever. With U values, because it's an inverse, higher numbers are worse, which is even more confusing. If you're listening and you're confused, just know that my architecture students are confused by this. I mean, everybody gets confused by it, but shopping for windows by U value is a great way to look at the energy, but you want lower numbers generally.
Our target was 0.14, 0.18. That's that. And every window will have a different value, right? Because of the frame and the glazing, the ratio between those two things. So you can't say all my windows are 0.15 or 1.3 because it will be a whole range. So we try to optimize that. And we are hoping we still have to do blow tests and things like that to figure out how much the seepages are, what are the leakages. And now we have the basement. We talked about the walls. We talked about the windows, which are going to help us make and balance the energy consumption in our home. Is there anything else that I missed?
A couple other things just worthy of mentioning. One of the ways to save money on windows is if the manufacturer has standard sizes, stick to their standard stock sizes. Obviously, that's going to be cheaper. You can make a custom size window in any size, but it jacks up the price considerably. We tend to only do custom windows when we're dealing with an existing house and trying to, match something going into an existing opening. And then the other thing, as you noted, is changing from an operable window, whether it's, double hung or sash or casement or whatever, to a fixed window. Fixed windows are less complex and therefore they're cheaper. It's also nice to be able to open windows where you want, but, be more mindful of which are the windows that really, that you'd open and use, and which are windows that don't need to open. That being said, any window that's in a bedroom, generally you need to have at least one operable window in a bedroom because it's also used as a fire escape in the event of, God forbid, fire. So, it's not like you can just say no operable windows anywhere, but it's all a balance.
Thank you again, Eric, for coming on Mindful Businesses. It's always enlightening and fascinating to hear your answers and learn from you, and ready to take on the next building project.
No, it's fun to hear your insights. I mean, you're essentially going to be ready to become an architect as soon as you're done this project. It's fun to watch.
Thank you again. You're listening to Mindful Businesses, Our Sustainable Home, produced and hosted by Vidya Iyer. We would love to hear from you. Send us an email at info@mindfulbusinessespodcast.com. If you learned a thing or two from this episode, share it with one friend. Click on the subscribe button to be the first to learn about our latest episodes. We recorded this podcast in Buffalo, New York. Theme music was composed by Tatum Gale. Roseanne Korean is our marketing assistant. Ketan Karat is our podcast editor. Our advisors are Jim Stone and Anupama Pasruja. This is Vidya Iyer with Mindful Businesses.